Let's just do a little review of Ohm's law, which governs the flow of current through resistances under an applied voltage. You'll remember that the voltage is equal to the product of the current and the resistance. So what that tells us, for a simple circuit where we put two resistances in series so that they add together, if we apply 5 volts from the UNO up here and ground 0 volts down here, then the voltage Vm in the middle here will be somewhere between 5 volts and 0 volts. So let's call this resistance R1, some number of ohms, we don't know what it is right now, and R2, but they're both fixed values. The total resistance will be the sum of the two, R1 plus R2, and we can look at the current flowing. Because it's a single path, any current that flows in here flows through that resistor, flows through that resistor as well. So all the currents are the same. So the current, I equal to V over R, will be equal to V1 over R1, and that'll be equal in the same way to V2 over R2, and to the total voltage, V total over the total resistance from here to here. So if we look at that, we're going to wind up with V1, well, that's the voltage drop from here to here. That's 5 minus Vm. 5 minus Vm divided by R1 equal to, well, Vm, the voltage drop across here from Vm to 0 will be just equal to Vm divided by R2, and those will both be equal to 5, the total voltage, divided by R1 plus R2, the sum of the two resistances. So as a result, we'll expect the measured voltage in between to be equal to 5 times R2 divided by R1 plus R2. Just going from this equation here, these two values here. So if we knew the resistances, we could find out the measured voltage, or we could invert this, and if we knew the measured voltage, we could find out the resistances. Now this is a really practical circuit, not so much when we use fixed resistances like this, because that's a boring situation, but if we go and we use variable resistances, then we can produce a circuit that's normally known as a voltage divider. And what that does is it takes the 5 volts that we have up here and divides it across these two resistors. If this is some known resistance R2, and this is a cadmium sulfide photocell, then its resistance will vary. And our measured voltage coming out of here will depend on the ratio between the CDS cell, the photocell, and the resistance R2. So by choosing an appropriate R2 to match the resistance of the cadmium photocell, then we'll be able to get a measured voltage coming out of here that tells us about how much light is falling on that photocell. Likewise, if we put a potentiometer in our circuit and put 5 volts on one side and 0 volts, ground on the other side, then the middle pin on that potentiometer is the wiper pin, and basically it's moving back and forth along that resistance. So we can vary and have R1 on this side of the wiper and R2 on that side of the wiper, and the result is Vm will go anywhere from 0 to 5 volts, depending on the position of the potentiometer. Because basically we're going from down here where R1 is huge and R2 is 0, up to here where R2 is huge and R1 is 0. So anywhere in between, if we were halfway in between, we'd wind up with 2.5 volts there. So we're going to keep on using Ohm's law. It's something you're going to need to remember from physics and hold on to throughout your career. And most of the time we'll be using it in really simple situations like this, 2 resistances in series or 2 resistances in parallel, or other relatively simple circuits. And we'll be using these to get measurement information out and see how resistances are changing in our sensors.